Okay, good afternoon, everyone. Good morning, depending on where you're located in the world. Thank you for joining us today for our webinar, Complete Building Design using Risa. My name is Ben Follett. I'm the Product Marketing Manager at Risa. And so I'm really excited about this topic. I'm really excited to show all the integration for those of you who've been kind of hanging in there with us through our recent release schedule. You know, we're really happy to have integration fully back in the products, and are going to really look to go through that today. And so before we get into the bulk of our presentation, which will be live demo, I just want to talk a little bit about Zoom. If you're not familiar with Zoom, if this is your first time using it, if you're having any audio issues, you can enable either phone call or computer audio just using the audio features. You can also use the chat. But if you do have questions, my colleague Ashley Adams is actually on the meeting with me. Instead of using the chat, please try to use the Q&A. That's just the easiest way for her to directly answer individual questions. That can be then kind of sent out to everybody. So use that Q&A feature to ask questions throughout. We may have some time to answer questions at the end, but most likely get those questions in during the presentation so that they can get answered while that's fresh in your mind, and we'll go from there. Today, we're really going to focus on a complete building design. So I'm going to start in Revit, transfer to RISAFloor, jump into Risa 3D then for lateral system design, and then jump from Risa 3D into each Risa Foundation and RISAConnection. So we're really going to cover a lot of ground today. We are recording the webinar, and so that will be posted on YouTube and on our webinars page, most likely with the holiday early next week. That'll be the same time that we'll send the PDH credits. So just bear with us as we get all that in there. We'll send you the PDH credits early next week after everybody gets back from the holiday. And so without further ado, I'm going to go ahead and jump into our live demo. And so what we're doing here is we're going to go ahead and start with our Revit model. And so in our Revit model, we have the you know, just kind of a basic, I'll call it a basic structure. Nothing too simple, but at the same time, I think kind of representative of maybe your typical office structure, steel office building that you would find, you know, in a lot of different places in the United States. And so we've got a couple stories. I've got some concrete walls. We've got some moment frames. We'll add some brace frames. I've got some other concrete walls in the back here. If we go ahead and look at maybe one of our middle level floor plans, you can see just kind of the basic layout. So nothing too complex, nothing too crazy. But we're going to use this to start to build our model. And doing so, we find that, you know, a lot of the people that we talk to that are doing building design, that are using Risa or somebody else to do full building design, most of the time they're starting with a Revit model, or they would like to start with a Revit model, right? And so it may be that they just don't have enough experience in the link, or they don't feel confident in the links or how they've built their models, that they just don't try it. But I really do think if we can nail down the way that the softwares work together, considering that you're documenting a lot of times in Revit anyways, or your architect is starting in Revit, this can really be a great time savings. And so let's look at a few things really quickly in the Revit model. So the first thing is we obviously always want to make sure we've enabled the analytical model. So if I go ahead, I just open up the floor plan for that level 1 for the analytical model. The analytical model obviously different from the structural model in that it has some different information. This is where all our alignment really comes into play. This is basically that center line matched, analytical line matched model that's going to be transferred with Risa 3D, RISAFloor. You can also see that there's some additional properties when you look at analytical objects. So for instance, we can choose whether the object is analyzed as gravity or lateral. That's an element that'll directly go into RISAFloor and set that model up for us. We can choose whether a beam's composite, right? We can choose the releases on a beam. So I know that this wants to be pinned. So basically the idea here is that I can define some of these things before I even have to go into RISAFloor, so that I don't have to do it twice, right? So I don't have to be making model modifications all the time. Now there's other objects, or there's other items that you know, we can look at. You know, we can look at different analytical floors, you know, how they're modeled. Are they elevated slabs? Is it a structural floor? If we go ahead and look at one of the walls, let's open up a 3D view here and look at one of the walls here. We've got some additional properties for If we wanted to define wall width, or if we had a wood wall, we could have sheathing and stud spacing and stuff like that. All information that could then be transferred into RISAFloor and Risa 3D for final analysis and documentation. Now, I'm going to go ahead and jump into our add-on section. This is where the link lives, right? This is the link that you would download off of the Risa customer portal. The link, the Risa Revit link, is a free link. It's a free plugin. It's built on the API between Revit and Risa, so there's no cost to that link, but you do need to have full versions of Revit and Risa 3D or RISAFloor to use it. Right now, we have current support for Revit 2021 and Revit 2020. Usually they change things, and so we keep up to date with 2 releases. If you need an older version, we can get that older version to you. It's just that there may be some changes that were made in the newer versions of Risa that, you know, like cold form steel walls, that the older link may not support or something like that. So, you know, you just have to make sure that you're kind of matching the functionality in that way. But if we look at the Revit link here, we're not going to talk about connections in this case. We're just going to look at this import export. And so I'm going to choose export because that's really what we're doing. We're starting with this Revit model. We want to export this Revit model into Risa to use it, right? And so the first thing we see when we open this up is we're going to choose what product we want to launch into. I'm going to start with RISAFloor because that's where our gravity members are going to start and our gravity model and analysis is going to happen. We can choose to export only selected items if we wanted to. So we can go ahead and use that as well. We also choose the elements we want to link. So if you only wanted to link walls, or you didn't want to include project grids, or you didn't want your elevated slabs, these would be concrete floors, or if you didn't want foundation slabs. I don't put a lot of loads and load combinations, but if you did put those into your Revit model, you could send those as well. You can choose those different elements to add. Also, there's some basic options. One of the ones that I always like to make people aware of is this RISAFloor design methodology. So generally, RISAFloor is going to do optimization, right? So it's going to be, hey, you define a wide flange beam, and then RISAFloor is going to pick based on the loading and the spacing and everything else incurred, what kind of beam that is. You know, is it a 12 by 26 or is it, you know, a 14 by 26? It doesn't, you know, we don't know. Or if you have specific sizes set in Revit, maybe you're doing more of an investigation, or you're looking at an existing model, or you're adding on to an existing model. This is where we can choose that we want to analyze sizes from the Revit model. We also have an advanced tab. There's just some label information, some tolerance stuff that we can set and change. We could also restore the default settings. But at this point, we're ready to exchange. The exchange happens based on mapping tables. The mapping table is basically an Excel file that says, hey, this family in Revit is matched to this profile shape, profile library in Risa. And so we'll see the transfer. That's why this transfer happens one-to-one. That's part of the API. So I'm going to go ahead, and I also selected my model file. So I just have a blank RISAFloor. I call it office building webinar model file that I'm going to transfer into. So I click OK. Do I want to save my model? Sure, I can save it. It's not a big deal. And then the transfer is going to go ahead and start. So just doing some verification and then going through the total progress to export all the different objects in this particular model. And as it's doing this, it's creating the RISAFloor model. So there's no kind of model file saved for the link, right? There's no kind of, you know, Risa Revit link file or anything. It's just going to automatically build that model in Revit, or excuse me, in Risa. And we can see a little bit of a log here. If there were any errors, this is where we'd see those errors. In this case, obviously, I've kind of tested this out, so we don't have any issues in this particular case. But we can see the number of beams, columns, materials, walls, etc. Right? We can also open and save a log file. This is going to be a file that we could go ahead if we run into errors and we wanted to save that so we could look through that later, we could do that. In this case, I'm just going to go ahead and click OK. Now, automatically when I click OK, remember I said that it's going to launch into RISAFloor. So it launches into RISAFloor, and we start with our model. And so I have my different levels here. I'm looking at my floor, my roof level. I'm looking at individual, you know, levels on my model here. And we can go ahead and look even at our full model here, right? So pretty straightforward, pretty standard. This is what our full model looks like, right? Not a whole lot, you know, changed between, you know, the input from Revit and what we have in RISAFloor. And that's the idea, right? And so if we start to look at this here, we can go ahead. Now, ultimately, I brought model information in from Revit, but we could also model in from, you know, just by modeling in RISAFloor. So if I go ahead to turn on my graphical editing, you know, maybe, you know, in this case, let's just say, I'm going to go ahead really quickly and just, I'm going to go ahead really quickly and delete our just delete an item by clicking on it. I'm just going to go ahead. Let's turn off our deck here. And I just delete this hoist beam, for instance. If I wanted to go ahead and add a beam, I could just go ahead and click on Draw and Modify Beams. I could say, hey, I want a hot rolled shape. I want to draw it point to point, and I don't want to follow any design rules. I want it to be pin. That's fine, and I can just go ahead and use my snaps to draw in that hoist beam. Right? Very simple, very straightforward to model. We could do the same thing with walls, or we could make modifications to members. So if I go down to level 1, maybe I want to click on this wall here, and maybe I wanted to add an opening, or maybe I wanted to add in a window or something like that. So I could go ahead and say, well, here I'm going to go ahead on level 2 and put in, a window opening. Now we'll, make sure to make it the same size as the door opening so that we get our regions the same. And then I can actually go ahead and generate our regions, right? So we can see our different regions there as generated. Turn this off, turn this on. Our generated regions based on our opening there, right? So we can go ahead and add that different stuff there. Now, if I wanted to make some other changes, we could start to look at the model here. So maybe I go into my materials. If we look back at our concrete here, so this is a typical just kind of concrete cast in place. That's the material that comes generically in from Revit for these 10-inch walls. And so I'm actually going to go ahead and into our concrete table here, just change the F prime C, so just the strength of that concrete from 3,500 to 5,000 PSI. So just a quick and easy change that we'll start with in there. The next thing in general, though, that I want to do is I want to look at design rules. So design rules really are what govern kind of the way that the model is set, or the way that the design happens for a given member or a given wall set or something like that. And so in this particular case, I'm going to go ahead and open up our design rules. So let's start with member design rules. And I've established 2 very simple design rules in this case. So the first one is I'm just typical, basically everything in the model, right? I want my minimum depth of every member, whether it's a beam or a column or a wall, I want it to be 8 inches. So whether it's these HSS columns, or it's the beams, or it's the columns, I want them to be a minimum depth of 8 inches. Really, I just don't want any 4x13s. I don't want any 6x20s. I don't want any of those really small shapes, right? So I want a minimum depth of 8 inches. Additionally, I'm going to set up another design rule, and this one I'm going to call lateral beams. And so in this case, I want to say, what, for any of my beams that are showing up in my lateral system, and that's these beams that are denoted here in red, any of those beams that are showing up in my moment frames, essentially, I want those elements to have a minimum depth of 10 inches, right? And so I could set that as part of my design rule. Now I can change some other things. I could set my deflection criteria for individual design rules. I could set camber. If we had a concrete building with concrete walls and a concrete, columns and stuff like that, we could set up some rebar stuff. We can do that as well. But in this particular case, we don't have any of that. We will have some concrete wall setup stuff, so wall design rules, and we'll look at those in just a minute. And so we're going to use those pretty standard design rules there, and I'm going to go ahead and also, just from a visibility standpoint, I'm going to turn off my diaphragm. Even though I have a diaphragm, I'm just going to turn off its visibility for just a moment. And so let's pop over here and say show diaphragm edge. Okay, so now we can really plainly see now we can plainly see our different lateral systems. So we've got our walls are part of our lateral system. We've got our frames that are part of our lateral system. The next thing I want to make sure is I want to make sure that our members have those lateral walls, or excuse me, those lateral members have our design rule assigned to it. And so in this case, I'm going to go ahead into our, I'm going to go ahead and deselect everything. So I'm just doing a deselection. And then I'm going to go into our select elements by criteria tool. And under beams, I can choose a function. So I want to select every lateral element. So every lateral beam. And then I want to apply that design rule there. So I'm going to go ahead and say, come into our beams, and instead of drawing a beam, I can make a modification to a property. So I'm going to say modify property here, and I want to use this design rule and say apply the lateral beam design rule. That will make it such that each member is no smaller than 10 inches deep, and I want to apply that to all selected beams. So I click apply, and now if I go ahead and look at one of these beams here, we'll see they are fixed. So that end release came in because I established those as fixed conditions in Revit. You can also see that the properties here, the design rule is a lateral beam. And finally, we can see that I've turned off composites here, right? Because if I have that negative moment in a composite beam, you know, generally we don't account for negative moment in composite beams, so I don't want this to be designed as a composite. So now I can go ahead and I'll go through this a little bit more quickly. I'm just going to assign the same sort of thing on the other levels as well. So I'll deselect everything, select only my lateral members, and then go ahead and apply this property, this design rule property, to all selected beams. So I did that on level 2. Let's go to level 3 now. Same sort of thing, deselect, select everything based on its function, its lateral member. So selecting those 4 frames now, and then go ahead and apply these design rules. Let's do it on the last 2 floors here. Again, running through the process. Now we could have done this in our spreadsheets as well. So I could have gone through level by level in my spreadsheets and I could have applied this design rule to each individual level. But in this case, I generally like to use graphical tools a little bit more than I like to use the spreadsheets. I feel like it's a little clearer about what I'm applying and where I'm applying it to, rather than trying to kind of look through individual levels of a spreadsheet. And so in this case, I can just really quickly and easily do that and then confirm, okay, it is a lateral member and it does fall to that lateral beam section. So we've got everything that we need here. I'm going to go ahead and turn everything back on. So now with all of those lateral elements set, I'm going to go ahead and let's go ahead and look at our wall design rules. So I'm going to go ahead and click here in data entry and open our wall design rules spreadsheet. And so this is our spreadsheet for all the various wall panels that we have. So we have concrete walls in this particular, wood walls with studs, or if you had cold form steel walls with studs, that's our newest wall panel. You can include those as well. So if I look at our concrete wall rebar, we can see our vertical bar size, our bar spacing, all the different bar parts. We can also see miscellaneous, basically how we want bars. Do we want them in each face? Do we want them in the center of the wall? What's the outer bar? Is it vertical? What's our cover going to be on the inside and outside faces? How do we want to transfer in-plane and out-of-plane loading? So different things that are a part of that kind of design criteria for those individual walls. And so again, if we had different wall sets, if we maybe had one concrete wall set that had one set of criteria because it was an 8-inch wall, and one concrete wall set that had another set of criteria because it was a 12-inch wall, we could go ahead and add different wall design rules to do that. The last thing I want to do is I want to use what we call a design list to basically kind of refine the design that we would do for our steel columns. And so in this particular case, I'm going to go ahead and open up our column stacks. And so if I open up my column stack spreadsheet here in the data entry, we can see that this is each column stack, just the stack label based on the grid system, where it's located, what's the length. So we have the different lifts. It's basically just the different levels. So level 1, 2, 3, 4, and to the roof 5th. And so we can see those elevations. And so we see here the different functions. And we haven't changed that design rule, but we do have this shape. And the shape is basically the design list. It's basically, it's going to choose to optimize a shape based on whatever that list is. And so in this particular case, it's our wide flange list. It's just going to look through the entirety of the wide flange list. And you can change the list. You could comment out different shapes to say, you know what, I don't ever want to design a column that's a 4x13. You could do that if you wanted to, or we do have some pre-built kind of specific lists built in. And I'm going to go ahead and use one of those for our lateral columns. And so I'm going to go ahead and choose our, you know, just in this particular table, in this particular fashion, I'm going to say I want to fill block. Basically, I can go ahead and type, and then I'm just going to type in WF space 10. Basically, in that case, what I'm going to do is I'm going to say every lateral column in this, basically in these lifts on these 2 locations, I want them to be designed out of my 10-inch wide flange database. And so it's going to take every W10 and it's going to look in to find the best case member in that case. And so I can keep doing that in the rest of this table here. So I'll find basically the other frames, the other brace frames or moment frames. So here's based on this lateral function over here. So I'll just say, okay, so the next one is here. Here's our next one. We'll say fill block again, WF10. Okay, we do have some laterals here, but these are our square tubes. So we're going to leave those the same. So let's keep scrolling down here. And then we have 2 more sets down here at the bottom. So here's our first one. So we say same thing, fill block, WF10, and scroll down here. Here's our next one starting on line 95, fill block, WF10. So we've got everything that we need there. for those members. So I've done that for all of those different members now. And so now I'm going to get my design kind of controlled based on the criteria that I want for this particular case. So let's go ahead and close out of the column stacks. The next thing I want to look at is decking, right? And so if I look at our deck definitions, we have some deck defined from defined from the Revit transfer. We could go ahead and change that. So I can open up the material type here and say, you know what, I don't want to use the standard, I want to pick a specific database. So I can pick a Verco or a Volcraft database. In this particular case, I'm choosing a Volcraft 2 VLI deck. So that's just a composite deck. We can choose then in conjunction with this deck, you know, what's our overall slab thickness and slab layout. So in this case, I'm going to choose that we want a 5-inch normal weight concrete with a 2 VLI. I can also make sure that we choose the proper normal weight concrete and make sure that my stud height and my diameter and my stud strength is all what I want it to be. So I can click OK. So in this case, then I've got that. The next thing here is this metal roof deck came in again from Revit. In this case, you know, maybe I want to be an equal opportunity deck guy, and so we'll give Volcraft our composite deck, and we'll give Verco our steel roof deck. And so we have our decks then applied in that case. So that deck, those decks are what we would expect them to. We can look at the loads tab to see the self weight of those particular decks. We could also add additional weight if we wanted to, but you could end up adding additional weight to the floor. So you don't necessarily need to add it here. This would be specifically for different parts of the floor or the deck if you want to. The next thing with decks though is we need to see the deck that we have applied. So if I look at the roof in this case, we see, okay, this green line vertically, so we can see the span of this. This green lines represent our 1.5-inch metal deck, so that's good. We have what we want. We look down at our next levels, we have that 3-inch lightweight, or excuse me, 3-inch concrete over our 2-inch deck, so that works too. If I look down at level 1 though, remember if we look at the 3D model, we do have this low roof here on level 1, so we don't want our composite deck outside kind of at the extents of the building. We want our roof deck here. So I can go ahead and make that change. So I'm going to go up to our graphical editing toolbar, open that toolbar, and we want to choose to assign basically a different deck or edge property. So in this case, I'm going to choose that I want to use that metal roof deck, and I want to assign it plan vertically, so it's parallel to the x-axis, and I'm going to just draw it point to point. Click apply, and then I'm just going to go ahead and click the extents of this particular deck. Now, I just realized I made a mistake. I'm looking at level 1 right now. I don't really want this deck on level 1 because level 1 is actually the first floor. I do want this deck on level 2. And so I've actually already applied it here on level 2. And so we can see here just by looking at the model here, I can see that I applied this deck just by clicking on the points here on the outside of this low roof so that we have that low roof applied. So I've got a different deck now at the low roof level and on the interior of the building there. Now the next thing we need to do, so we have our model created, we've got our openings created, we've got our different decks, we've got our lateral systems, you know, positioned where we want them to, and we've got our design rules set up. We need to go ahead and look at loads. So the first thing I'm going to do is open up our area load definition spreadsheet. And so this gives us our uniform area loads that are applied to the building, right? And so in this particular case, this corresponds to, and if we can go ahead and open this up, this corresponds to our default loads here that we have. And so if I look at here, in this case, we can see that the coloring here, we've got a generic office load here on the different levels. And then in the same way that we applied our deck, we have a roof, or a low roof in this case, load applied here at this low roof. And so we can see that this office space here in this blue is 10 PSF of post-composite dead load, as well as 50 PSF of reducible live load. And then the roof is 10 PSF of dead load and 20 PSF of non-reducible roof live load. And so that load is then applied to this particular level. Now, if we wanted to add something different, maybe we wanted to add, you know, a storage space, you know, over here, and it was going to be 100 pounds a square foot or 125 pounds a square foot, or if you had some other types, you can go ahead and add to this list. If I just click enter, I can add another level to this list, and I would say, okay, this is going to be like, you know, library or something like that, you know, right? And then we could create, okay, you know, that different load that we want there, right? And so we can have exactly what we want, and then go ahead and just draw it into the level. So maybe if I wanted to do this, you know, I would just say, okay, library, you know, let's say that library needs to go, and I'm going to click on to add an area load. say I want library to draw point to point, and I'm just gonna put it on this level. Let's go ahead and maybe put it on another level. Let's put it on level 3 or something like that. And we can just go ahead and apply it. So let's just maybe apply it right here. Right, so it's going to overwrite that level. So it's going to overwrite that load at that location. You can do loads that are additive. So if I come back to this spreadsheet, you see this checkbox for additive. So we could do loads that would say, hey, in this location, I've got the dead load, and the live load, but I've also got additional piping load. And so we can go ahead and add that as well. Now we can always add other loads as well. So like if I go to the roof here, we can see that, in this particular case, I have a point load, a dead point load applied at this hoist beam for, the hoist, right? For the elevator. And so we can apply that load. If we wanted to apply maybe a line load or something, so let's say if I go to like level 4, maybe we have a partition or something like that, movable partition on a floor that we want to apply load. I can go ahead and say, in this case, I want to draw a line load, and let's say it's going to be in live load, and it's going to be 100 pounds a square or linear foot, excuse me. And I want to draw point to point, and I'm just going to go ahead and put a live, line load here and a line load here, right? I can go ahead and turn off our area load so we can see a little better. So now I've got that load there. And so that load is just going to be distributed to those connecting members based exactly on, the tributary area of this system. So we've got our line loads, we've got our point loads. The last thing that I want to do is I'm going to go ahead and look at our floor spreadsheet. The last thing I want to do is on that low roof, let's say that maybe we've got a brick ledge or something like that, and maybe we've got a parapet, right? So I've got a parapet load, or I've got a parapet that then I want to have parapet wind loading on that low roof. And so in this particular case, on our floor spreadsheet, we have this option to define our parapet height. And so when I define a parapet height, it's going to look for basically any part of the model that doesn't have anything above it. So if I choose in this particular case to say I want 4 feet as my parapet height on level 2, then what we're going to see if we look at the 3D model is we're going to see this orange line that represents that parapet on the kind of low roof. Now, because the rest of level 2 kind of inside where that office building structure is, we want to be able to look at that model there. We can go ahead and see that, because it had something above it, it's not going to put a parapet there, but it will put a parapet on these levels or on this outside part that doesn't have anything above it. So that identifies that as our low roof. If I go ahead and look at that, I can go back to our level 2 here. And then I can also look at let's go ahead and turn everything back on. And then I can go ahead and look at our ISO view, right? This ISO view gives me a good representation of, things just in isometric. So you get a little bit more. You could also turn on, kind of the column heights and stuff like that. Obviously, we could turn the rendering on to see, kind of how things are laid out here. I don't generally use the ISO view a lot, but I think it's just another option here for visibility as you're looking at an independent floor level. And now while you're working at floor by floor, these are all integrated together. And we'll see that as we push this into our RISA 3D model. Okay, so the final thing that we need to do, I'm just going to go back to a level here. Let's get off of our ISO and back on our plan view, is we need to create load combinations. So if I open up load combinations, we just have some standard load combinations created. I'm going to delete them, and I'm going to use the load combination generator. And so in our load combination generator, because we're only doing gravity analysis in RISAFloor, I'm just creating gravity load combinations. And so I'm going to create a 2018 IBC strength set of combinations. So no snow load, and I'll just generate those. So that gives me those IBC. I also do want to create the ASD because I do want serviceability. So I'll click generate as well. And then we can go ahead and look at the design tab. I can see, okay, and I could change this if I wanted to see, okay, for hot rolled steel, I'm going to do design using, the LRFD combinations. For wood and wood products, I'm not going to use LRFD. Maybe for masonry, we would want to disable and say, for masonry as well, I'm not going to go ahead and use LRFD combinations. I only want to design an ASD. And then you could also do the same thing with connections, which leads me to our ability to define connections, right? And so we're going to do some I'm going to go into Risa connection after looking at our Risa 3D model, but we can still assign specifically, it makes a lot of sense to assign gravity connections in our model here in RISAFloor. And so if I go ahead and turn on our visibility, I could say I want to look at my connection rules. And so I can go ahead and look at, our different level here. So I've got a few connection rules already defined. So in this case, I've got some column shear tab, column to beam shear tabs, and also some girder to beam single angle shear. If I go ahead and I click on a specific beam, I can actually see in our general setup here the start and end connection. So I could go ahead and define this. So, if I wanted to call this a double angle on one side and I wanted a double angle on the other side and click apply, right? I could get that column to beam double angle shear connection in there. I can do the same thing to apply those just by going ahead into our beam properties and choosing to modify. So I could kind of apply those in bulk, right? I could click on a bunch of members or have a bunch of members already selected and apply those in bulk. In this case, we're not going to apply too many different connections. We'll also look at assigning some connections in Risa 3D. But I just wanted to show you that even though I'm not going to transfer directly from RISAFloor into RISAConnection, I'm going to go to Risa 3D. This stuff, because this model is one model, because this RISAFloor model is kind of the place that this all starts and the place that this all lives, we're still going to have that kind of transfer of data, whether it's the load case information, whether it's the loading information, whether it's the connection rules. That information is going to follow us from RISAFloor into Risa 3D and then finally into RISAConnection. So now that I have that assigned, I'm just going to zoom out here and I'm going to go ahead and run my analysis. So I'm just going to solve my full analysis. Now, one thing I want to make sure of here, if I look at my general setup here, I just want to make sure that I have skip loading off. You can keep skip loading on, but for the instance of this particular model, this particular webinar, I want to keep skip loading off so that the solution runs a little bit faster rather than going through all those different iterations of skip loading for individual beams and individual columns. And so this is actually doing a full-blown optimization. So it's designing each and every member based on the loads applied and looking for the optimal shape based on those design lists that we created, whether it was those column design lists with a 10-inch wide flange, or it was just the regular wide flange or regular square HSS shape list that we allowed the rest of the beams and the rest of the columns to be designed from. That's what it's doing. It's going through that full-blown optimization to find us as well as doing the optimization for the elements. And so now I do have a few kind of warnings. So if we look at our warnings, sometimes they're just kind of a note. For instance, hey, it's saying, hey, your composite deck, you have a few, stud issues. So we could go ahead and change those. It tells us that we have a column that terminates over here and over here on top of a wall. So it's just saying, it's not a moment splice. It's just going to be a shear splice in that case. So that's okay. So we have a couple conditions, nothing that's going to prohibit us from continuing on with our design though. So let's go ahead and I want to say none here and let's see our design results. So we have our design results now. So we're looking at our design results and we can start to, check some different things. So if I wanted to, I could go ahead and look at our design summary. So in our results here, I could say, show us my code checks, right? So here's all our code checks. I could go ahead in our bending check and I could do a little sort here to see, okay, what's the absolute max and min? So it looks like we have a member, an 8x21, at a certain location. If we wanted to look at, this is in particular level 2, we wanted to go ahead and look at this element in a detail report, I can go ahead, select it and say detail report for current item. And so now I can get that detail report for this individual member. So if I turn on our load combinations, we can see, okay, here's the load applied, here's the shear, the moment, the deflection, no axial force because it's pin-pin, that makes sense. And then we can go ahead and see the capacity of this particular member, right? And so we can see, okay, the design rule, it had to be a minimum depth 8 inches, so it's following that design rule, the shear capacity, the bending capacity, and then deflection capacity. So we can go ahead as well as vibrations. We haven't talked a lot about vibrations, but it's doing that vibration check according to Design Guide 11, either the first or second edition based on what you selected. We can also go ahead and use our design tab. So we can go ahead and say, let's see, for a given member, so we say design here, we can go ahead and look at the design of this particular shape and see, okay, it chose a 12x30. Why did it not choose a 12x26? Okay, well, the 12x26 failed in bending. Okay, that makes sense. And so I can see the bending check and, what about a 12x35? Okay, so if I wanted to go up to a different shape, I could. If I wanted to make a change, I could definitely do that. But this is why it chose the 12x30. We can see that bending check up to that one unity level. So we can go ahead and click OK and keep that there as well. Now, at this point, we've got our design mostly complete, right? We've got our gravity analysis done, our gravity design done. We could go ahead and look at, some of our wall panel design, right? Our wall panel is just designing for axial. So in this particular case, our wall panel design is incomplete. But we could go ahead and look at the basics for axial in this case. The next step, though, is to finalize the design for the walls and also the lateral frames, these moment and brace frames, which we'll look at. We need to jump into RISA 3D. And so to do that, super simple. Like I said, everything works together to complete one model. I'm going to go ahead into the director up here in the right-hand corner, and I'm going to click to transfer into RISA 3D. So it wants me to save the model. That's totally fine. So I'll say save. And then once I save that model information, and I'm also saving the result information, the next thing that's going to pop up are our loading. So we're now jumping into RISA 3D where we need to look at wind and seismic loading. And so the first thing that's going to pop here is our wind load calculation. And so we can go ahead and choose the code. I'm going to choose the code and the wind speed that actually works for where I live here in Pittsburgh. And so 110 mile an hour wind speed, exposure category B. I'm going to use the most recent ASC 716 code, click Calc Loads. And then if I go ahead and look here, I can see at the different levels, including the parapet level, what the wind pressures are and what the size of those, leeward pressure zones are. And so we can see at level 2, for instance, that level 2 is at 24 feet, but the parapet there is at 28 feet. And so that parapet load is going to be included as part of level 2 load. So we can see the QZ factor and the additional force. So in the X and the Z direction, 10 kips and just over 9 kips that are going to be applied alongside of level 2. And so that goes into and will be applied as a separate load in our load distribution. So if we go down here, we can see, the different load here that's being applied based on those different zones. So in this case, I'm good. I'm happy with what I'm looking at from a wind load perspective. I'll click OK. The next thing that pops up here is the seismic loads. So not a ton of seismic here in Pittsburgh, but I've actually increased beyond what Pittsburgh would be. I actually doubled this because generally I'd be in a seismic design A category and it wouldn't really require seismic design, but we want to include that in the design so we can see this. So I've jumped out those loads a little bit from the using the online USGS calculators to get our SD1, our SDS, our S1, our TL factors. We can also set our R factor. I'm going to say that this is a system that's not specifically seismically detailed, which generally is an R of 3. So R of 3 in both the vertical X and horizontal Z directions. You could use something different if you wanted to. You could also set the period differently, but in this case, we'll calc those loads and get those shears at each individual level along with the base shear and the total weight of the structure. And so now that we have that information, we're ready to go ahead and click OK. And so again, it's going to write this transfer file, and basically it's going to write everything. So remember, we have all the results and all the loads here that are tracking through, and it's going to go ahead and write that information into our RISA 3D file. So while RISA 3D launches here, I can go ahead and, let's see, open up RISA 3D. So it should be just a second here, hopefully. But as it launches up, we're really just looking to create that model from RISAFloor. And I apologize, my computer is just going a bit slow today. It must be with our, with the connection here. So here, RISA 3D launched automatically. I didn't launch anything, it just opened itself. You can see right off the bat here, as this is initializing, you can see here that this model is a RISA 3D model that's connected with RISAFloor, so it knows that this information is coming directly from RISAFloor. So that's a good thing. We know that those models are connected, and we'll be able to have some different features because of that connected model sense. So because of the diaphragms that we had set, right, that information is going to come across, and we'll be able to view that here in our RISA 3D model. Additionally, if we had, when we look at the loads from the load generator, we'll be able to see those loads applied at the various locations at different nodes in our RISA 3D model. The first thing that we notice is that we don't have the full model, and that's because our gravity members are designed completely in RISAFloor. So we don't need to have any other reference to those members specifically in RISA 3D other than the loads that come alongside them. So if I go ahead here and click the Display Loads button, we can see all of the loads that are associated with a different load category. So in this particular case, we're looking at dead loads, for instance. So We're seeing dead point loads on the edges of frames where a beam or a joist frames into that column or beam. So you can see, for instance, over here, our framing direction for RISAFloor was in this direction here. So we have a point load, right? And they're uniform, which makes sense. So we have a uniform point load in this case, right? That's applied in this location. And so we're getting all those loads. All that load information is tracking from RISAFloor into Risa 3D, and then we'll continue to track it even down into Risa Foundation, as well as into RISAConnection when we look at our loads applied there. So we've got all of that load information. The other thing I'm going to go ahead and do is I'm going to turn on my diaphragms. So I'm looking at my individual diaphragms in this particular case. So just the diaphragm levels. Now, in this case, I've left everything as a rigid diaphragm. I could have gone back. I could go back and I could change this upper roof level to be a flexible diaphragm. And we can see that diaphragm information. If I go ahead and click on diaphragms in the Explorer here, we launch into this spreadsheet and we can see the different diaphragm types. So I can actually go ahead and flip this right here and just make this a flexible diaphragm. And so that's just going to change the load distribution for that particular diaphragm, right? So we'll look at that. That's no big deal. So if we go ahead and now we have our diaphragm level changed. I could also go ahead and look at our wind load as it was brought in. So if I look at our wind load X here, let's go ahead and turn off our diaphragm and let's go ahead and turn off our nodes. Oops, wrong way. Turn off our nodes here. We can see the different nodes that those loads are applied to. So this is that node that's kind of in the center of rigidity, center of mass of the structure. We could also see kind of our partial wind loads here. So using a different node to give you partial wind load X in the X1, X2, same sort of thing if we go ahead and look at our earthquake load in the Z direction. Same sort of thing. We're using our main load there, our main node there, and then we also have the plus or minus eccentricity. So we've got that 5% in this particular case, eccentric loading that's going to give us that moment at each individual level. And so we've got all that there. We also have our design rules. So if I look at our member design rules, those member design rules are transferred in from RISAFloor. So really, the different programs really are being used to model and evaluate the same structure. They're carrying through loads and design criteria. And it's really just allowing you to look specifically at the part of the model that you want to focus on in that particular software. So whether it's gravity analysis and modeling in RISAFloor, or it's lateral design and other kind of specialty elements in Risa 3D, or it's foundations, connections, it doesn't matter. It's just really just giving you a smaller window to focus your view to make sure that you get exactly what you want in that particular model. And so those design rules are coming across as well. So let's go ahead, actually, let's go ahead and change one of the design rules. So I'm going to say member design rule, let's set this, let's set our unity check for bending for, maybe our lateral beam to, 95%, right? So we don't want to go all the way up to 1, we want to go to 95%, so we can keep that there. So now at this point, we could go ahead and model in additional parts of our structure. So, maybe I wanted to, in this case, I've got some braces already modeled in. I could go ahead and model in some other braces. So maybe we want to put some braces on one of these small frames here. And so in the front here, this is our HSS. So if I go ahead and turn on our rendering here, this is our HSS here. So maybe I want to do some HSS braces. So I'm going to go ahead and click on Draw Members. So I'm just clicking the Members tab. And now I want to go ahead and define maybe a new section set. And so section sets just used in this particular case to define basically a group of members that are going to follow the same criteria. So let's say I want to create a new section set, and let's call this HSS Brace. And so the shape size that we're going to start with in this particular case, maybe it's going to be a, let's say a rectangle. So let's say a tube. And then we can go ahead and choose that tube. I think these columns are 8 by 8, so we can choose really anything that we want. Maybe we'll just choose a 4 by 4 by 4, be pretty standard here. The member type in this particular case is a vertical brace. The design list we want to use is we want to stick to a square tube. The material is going to be that A500 grade B rectangular, and we'll keep the design rule as is. Click OK. And so now we've got that element. We could go ahead and just model in. So I'm just highlighting over the node and just clicking the start point and the end point. Same thing, start point, end point. I can keep going on this one. So let's just make sure we get the node here and then do the same thing, start point and end point. Now, if I wanted to, I didn't make the change here yet, but very similar in the new interface to AutoCAD and Revit. If I want to go modify a member, I can just go ahead and select. I'm holding in this case now, Control and select to multi-select. And then I'm just going to come in and maybe I want to add releases. So in my I release, I'll change, and my J release to choose to pin pinned. And so I can just pin the ends of those braces so that we can, do the analysis and design. So now that I go ahead and have, the other thing I could add here is maybe I want to change my tension and compression, right? So I can make them tension only, I can make them compression only, I can allow them to be both ways. Maybe it can't take a lot of compression. I like to use this Euler buckling. Basically, it can take a little bit of compression up to its Euler buckling, and then after that, it's all in tension. And so I think that's the most realistic of what we truly have in the model. That's really the way that the element is going to perform if it sees a little bit of compression load. So I'm going to go ahead and keep it like that. So now that the structure is essentially modeled, right? We've got the modeling information here. We could go ahead and assign our load combinations. So I'm going to go ahead and click load combinations here. And I don't have any, but I'm going to create new load combinations using, again, our load combination generator. So I can go ahead and click the generator, and we're going to generate gravity, wind, and seismic load combinations. So I'm going to choose to include the deflection load combinations, but I'm going to choose IBC strength level combinations. So I'll click generate. So we'll get those gravity combinations for wind. We'll just choose X and Z. And I don't need to enter any of these additional options, so we'll just choose generate again. And then finally into seismic, let's just choose X and Z again. We could go ahead component or non-orthogonal, but in this particular case, let's just keep with kind of the standard combinations and do that. So now that we have everything there, again, we can go ahead and look at the design criteria. We could set different combinations to do different types of design. In this case, I'm going to keep everything exactly as it is. And I'm just going to go ahead to choose to solve the batch and the envelope load combinations. And so this now analysis is going to start to do it's going to use the processing cores of my system, and it's going to solve the model, based on, as many cores as I have in my computer. We can actually set that. So in this case, you can see here, I actually have a 16 core machine, but I've chosen that it's going to use basically half my cores. That's what we call the optimum setting. And so it's going to utilize half my cores to continually run in parallel different load combinations and run them over and over, run them again and again during the different parts of the design. And so it's doing that, finalizing the design for the members, and then finalizing the design for the wall panels as well. And so once this is finished here, we can go ahead and start to evaluate our design results from a combination of the gravity and lateral loads in this particular case. And so with that, we should then get our new, our Explorer should change and update to add our results-based spreadsheets. So we have our data entry spreadsheets, but we'll also get our results-based spreadsheets here. Okay, so the first thing I'm always presented with is just our envelope node reactions. We can evaluate those, but I'm gonna go ahead and close those out. And let's start to look at some of the other results. So the first result I wanna look at is I'm just gonna look at the code check spreadsheet. So I'm just gonna come down here and look at the envelope code check spreadsheet. So here's our code check spreadsheet. I'll expand this a little bit. And I'm just going to go ahead, right click, sort, and say sort absolute max domain. And so we have a few failures, and that's okay. It's not overly surprising, right? Because initially some of the members were designed for only the gravity load in those lateral systems, and now they're getting lateral load in a brace frame or a moment frame or something like that. So in this particular case, we may need to make some changes. And so if we do need to make some changes, we could either apply those on our own, or we could go ahead and use what we call suggested design. I can also look at the same results graphically. So if I go ahead and choose on our home tab here under quick view, I can go ahead and select our member colors and say, I want to show the unity check. And let's go ahead and turn off our loads here. This is a unity check. We're looking at a single combination here, but I actually just want to look at an envelope. And so now it's pretty plain to see, kind of where our problems are, right? So, okay, it's in this particular moment frame over here that we're getting a little bit of overstress, right? And so we can go ahead and choose, well, maybe we want to see why this particular member is getting overstressed. What's the failure mode in that particular case? And so here, I'm going to go ahead and click on the detailed report for this. And I'm going to go ahead and click this member. And then it's going to launch into the detailed report. And this is one of the great new features in the latest release and the latest interface of Risa 3D is the ability to look at truly the detailed report of a particular member. And so I'll just make this a bit smaller. And now we can see, okay, all the basic data, that's fine. We can see all the diagrams, and we could go ahead and expand the diagrams and look at them as well. But really what we want to look at are the limit state code checks for, in this case, 360-16. And so we can see here, okay, we're failing in combined axial and bending, but if we look here more closely at our required available values, we can see, well, most of this seems to be coming from flexure, right? So we do have probably about 50% utilization in our axial compression, but we do have a lot of strong axis flexural bending. And so we can go ahead and look step by step, right? Basically, as if you were doing a hand calculation in your steel design course in college, what are the steps that you would take to evaluate this particular member for flexure? Here's what we would do, right? We'd check LTB, we'd check the slenderness ratio for flexure, right? We'd check the yielding, we'd do the lateral torsional buckling check. We'd come through and we'd look at all of this stuff to get to our allowable flexural strength for the strong axis bending. And so we'd see, okay, here's the governing value, here's what we have, here's what we're allowed based on our reduction factor, and that's what gets us ultimately. So really, this is great. You're not going to evaluate or look at this level of detail for every single member, but if you're looking at a member and you're saying, hey, I don't quite understand why that's failing, right? I didn't expect that to fail. What's Risa doing? It's really plain to see exactly how Risa's handling this, right? And so if we wanted to then say we wanted to make an update, I'm going to come over here into what we call suggested design and just look at suggested design in this case. And so we could go ahead and look to see, okay, well, some of those members, it's suggesting that we change the current shape to a different shape, and then we're coming in here and we're changing our some of our other shapes. So this is up and down, right? This is it's not just if some are over designed or under designed, it's including both of these things. And so it's including some of these shapes that are really small, as well as some of these shapes that are under design. And so in this case, if we would resolve with the suggested shapes, we would go ahead and go through that resolve process. It would use this suggested shape. We could choose whether or not we wanted to use a design and say, you know what, I'm okay with this angle that we're using, so I don't want to change it, I don't want to keep it. We can go ahead and do that. In this case, I'm not going to spend the time to do that. And the last thing I want to look at, though, is I'm just going to go ahead and open the detail report in this particular wall panel. So I do have a failure in this wall panel. It's because I added this opening on the second floor. So I'm not overly surprised by that because I didn't make any changes to that. But essentially, we can see now from this particular wall panel, we're starting to get in-plane and out-of-plane design. And so really, I'm showing that I'm failing in plane. We can choose the different governing load combinations as well as the unity check. So the unity check in region 2. So I can come down to region design, and we can look at our region here. So I'll expand the region, and we can see exactly why this is, what's happening here. So again, not as detailed as the steel code checks or the 1D member checks in this case, but still giving you a good amount of data to try to figure out exactly why something is being designed the way it is and exactly why it's failing. So in this particular case, we have plenty of axial, but really our moment capacity is where we're falling short. And we can also look at, how this is being detailed. So we can see the cross-section detailing, we can see interaction diagrams for this particular thing. So we can look at all the data, and then if we want to, include this data with our full report. And so we could do that. I'm not going to spend a lot of time looking at reports because I do want to jump into the other softwares, but we could go ahead and document with all of that. So at this point, we're making the assumption that we've finished our design, we're ready to go, and we're ready to kind of jump into Risa Foundation and RISAConnection. Now, before I do that, I'm going to go ahead and turn off the visibility of just some of these labels, and I want to show I do have some connection rules defined. So in this particular model, we have a diagonal vertical brace, right? So I have wide flange with angled braces. We also have a column beam, flange plate moment connection. Maybe I want to assign something else. So I'm going to come back here and say, let's say at this column and this column, we're going to go ahead and assign RISAConnection properties here in the properties panel. And we'll say that at the start of both of these, we're going to do a single column base plate. Right, so we have that single column base plate now assigned there, and we're going to be able to transfer that information, transfer that data into RISAConnection. So now with all of that connection, data defined, and we've got all of our loads, right? We've tracked all our loads from RISAFloor into Risa 3D, all our gravity loads, and now we've applied all of our lateral loads, right? If we look at our lateral loads, we can go ahead then and take this into Risa Foundation. So I'm going to go again into the director, and I'm going to say I want to go to Risa Foundation. And so it says the model must be solved. That's fine. So let's just go ahead and I can actually just run a single load combination solution in this particular case before I'm going to go ahead and recreate load combinations in Risa Foundation for use of Risa Foundation. So I'm just going to run one combination so that we have basically the load cases are generated there. Okay, so the load cases and the load distribution has all happened. Now I can go ahead and jump into Risa Foundation. So again, do I want to save the file? Sure, I do. And I'm going to do the same process, same transfer process. This process is getting, or the model and all the information from RISAFloor, Risa 3D is being tracked over now into Risa Foundation. And so we're tracking that into Risa Foundation so that we can then look at basically the boundary conditions. Now, this is just a warning. In this particular case, it's not going to change much, but it's just telling us that Risa Foundation is not considering the effects of tension and compression members. So it's just saying, hey, we don't do, basically a pseudo nonlinear analysis in Risa Foundation. So your loads might be a little different. So it's just a little warning in that particular case when you're looking at that. But in this type of structure, I don't think that we're going to have any issue. So now here, we do have some, I'm going to go ahead and, I apologize, we see some of our loads here. So I'm going to go ahead and delete all of my wall footings here, and I'll delete also delete all of my actual footings. So let's delete all of our, footings there. Okay, so we've got all of our footings deleted now. And so we can see the information that's come across. So we've got our dead load, our live load. If we look at like let's see if I look at our earthquake load, right? So we can see that gravity columns where we didn't have a lateral system, no earthquake load there. That makes sense, right? Because the earthquake's only going, the seismic load, the lateral load is only going to those lateral parts of the lateral system. And so with that, we can start to define criteria here. And so I'm going to go ahead and first create load combinations. So let's come into load combinations. I do have those already created here in this particular case. So again, just using the same load combination generator, I'm using to create IBC strength and serviceability combinations. We can choose seismic load combinations as well as overstrength combinations, as well as wind combinations. We can choose a new feature in the latest release of Risa Foundation is the inclusion of, if you were doing a response vector analysis in Risa 3D, you could include those results as well in the analysis here into Risa Foundation. But in this case, we don't have any RSA, and so we're just going to do kind of our grouping of gravity, wind, and seismic, both service and strength combinations here in Risa Foundation. Once we have our combinations created, the next thing we need to do is we need to assign footings, right? So we need to, assign the footings that we have so that we can, apply the loads that we need, right? And so in this particular case, let's go ahead and choose to assign our basic footing. So footing one is defined in this case in our data entry. So if I look at footing definitions here, we can see the basic properties from a general standpoint, but really what we're looking at is our geometry. So going from a 2-foot to 10-foot length and a 2-foot to 10-foot width, increasing by half-foot increments. We can force it to be square. That's what this one is. And so just setting up criteria for the geometry. If we have a pedestal, what's the pedestal? What's the soil criteria? And what's the basic reinforcement criteria? And so we're going to go ahead and set that up. And we can apply different footings, but in this case, I'm just going to use that same footing. And again, this is actually an optimization, right? So we're doing an optimization here in this particular case. So it's looking at all of these, looking at this size and this criteria, and then saying, okay, well, I'm going to go ahead and try to find the best size footing that works for the criteria that you have, right? And so I can go ahead and, create that information. So now I go ahead and, missed one here. So let's put this guy back in here. Let's get rid of those ones. Okay, So now the next thing I'm going to do is I'm going to go ahead and put in our wall footing. So here's our walls. It's maybe a bit easier to see with our loads off. So here's those L-shaped walls. So I'm going to go ahead in this case and choose to draw or modify a wall footing. So now I can make it a simple strip footing, or in this case, I can go ahead and look at our retaining walls. So in our retaining walls, we can set up all the criteria of our retaining walls, both the geometry, all the soil criteria, all the detailed information for the reinforcement. You know, if we wanted this to be a masonry retaining wall rather than a concrete retaining wall, we could set that. So all the criteria we're establishing for the design of retaining walls, and then it's going to do the full design of the retaining wall in this case. So I'm just going to go ahead and just kind of match the extents of the wall. So just going to go ahead and draw from one to the next point, and then let's come down here to get this last one here. One point to the next point, and we have that. The last thing we want to do is we have our kind of a core wall here. And so instead of putting wall footings under the core wall, I'm actually going to put in a mat slab. Basically, it's just a big raft foundation. So I'm going to choose to draw in our slab. We can choose the thickness. Let's make it, I don't know, 14 inches thick. And I'm going to go ahead and draw this slab from our slab edges. So let's go ahead and just draw it at the edge of our walls here. Oops. So there's that slab. Now we don't want our walls to terminate right on the edge of the slab. That obviously doesn't make a lot of sense. And so I'm going to go ahead and use this nifty little tool that allows us to offset the edge of the slab. So I'll just choose to offset 3 feet, and I'll just click to apply on all slab edge distances. And so we've got those edge offsets that we need. Now if we go ahead and start to look, we can go ahead and maybe maybe we want to, in this particular case, I've got a column here that I missed. We could even choose to offset this slab even more. So maybe we want to offset it another 2 feet, right? So that we can incorporate, this column here, right? Because it's so close to that wall. It's really up to you. And a lot of that has to do with how you want to model that slab in. So now at this point, basically we're ready for our analysis. So I'm going to go ahead and just make sure, I'm just going to go ahead and I don't think we need these nodes here, so I'm just going to go ahead and get rid of them so they don't really cause us any issues. We'll get rid of these guys too. And we can do the same thing with these ones here. They were just from that original. And then we can go ahead and run our model. So it's just going to go ahead and run. It's using the same kind of parallel processing, so it's utilizing a various number of cores to run individual load combinations at the same time in parallel, so the design gets done quite quickly in this particular case. And so once this is done, we can begin to evaluate our results that it's giving us. Okay, so now we have some results. Now it is telling us, we have a few just kind of warnings. So it's telling us some of our retaining walls are failing either strength or serviceability. So like, let's go ahead and start there. We can go ahead and start by looking at the detail report of our retaining wall. And so I'm just opening up that retaining wall. And so if we zoom down here, we see, okay, we have a soil bearing failure. So I have allowable bearing capacity of 5 KSF, and there's a few spots that were just slightly over. So, we may need to, in that case, then increase the size of the footing in our retaining wall, right? So I can come into, in this particular case, come into our wall footing definitions, and we're looking at wall footing 1, I believe is what we're looking at here, and we can validate that. So if I come in to look at our wall footing, let's see. We can go ahead and see that, let's look here in our data entry is where we want to go. So let's say wall footings. So they're all wall footing 1. And so if we look at our wall footing design rules, basically, we can see the geometry of this. So the footing thickness 18 inches, toe, so basically it's 7 foot. Let's go ahead and change this to, I don't know, 4.5, oops, 4.5, and we'll lose results, and that's okay, and 4.5. So a little bit bigger should hopefully allow us to solve a few of our bearing capacity problems, right? And so we should then hopefully get some design for these different retaining walls. And so again, this is doing an optimization, and we'll see that I think the most obvious way to see that is when we go ahead and look at our individual spread footings. And so right now they're just look like a standard square, but after the design is complete, we should get different design sizes, and we do. So we can go ahead and start to look at again, the detail of our footing wall here. So we can see, okay, that solved the issue with our bearing capacity problems. And so we can start to see, okay, we do have some sliding issues. So we can start to, maybe we add a key, maybe we do some other things in the model there, but we can see all the different parts of the calculation that are being done for this particular retaining wall. We can do the same thing in looking at our spread footings. So again, spread footing here, 4x5 spread footing has been optimized based on the criteria. It's got all these different soil bearing conditions, so it's optimizing it based on what it needs from a soil bearing perspective. It's then highlighting in green kind of the controlling reinforcement requirements, so flexural, shear reinforcement, doing our pedestal design. So in this case, we've got a 12x12 column, or a 12x12 concrete pedestal that the column sits on, and then doing our overturning and sliding checks. Now the final thing here is we want to do the slab design. In order to do that, I need to define a design strip. So plan horizontal, so we'll just put in a design strip here to design the horizontal reinforcement. And then same thing, except I want plan vertical in this case. And basically just going to design this as if it's a concrete slab, in this case 14-inch thick concrete slab, and we can go ahead and look at the results of this slab design. So we can see it's just doing various cuts. In the detail report, it's doing various cuts along, along the length here, and it's pulling out from those cuts what's the worst case, and that's going to be the worst case that is used to design that strip. Now, if you needed to do different strips, you could do that as well, but in this case, we'll just use kind of one here. Now, all this information obviously can be documented in a variety of different ways. We can actually export a bunch of different things as DXF files to include maybe with your footing details in your AutoCAD or your Revit model. But in this, or we can include reporting PDFs back into our full Risa 3D model, or you can print PDFs from Risa Foundation. Now, the last thing I'm going to do is I'm going to jump back into Risa 3D, and we want to jump into RISAConnection really quickly. So I'm going to take about, I don't know, five or so minutes to jump back into RISAConnection. And so we're coming back into Risa 3D because that's kind of our hub. That's where everything lives, and we define those connections both in RISAFloor and in Risa 3D, and then we'll be able to go ahead and transfer then the connection information as well as our end reactions from a variety of our combinations that we ran in Risa 3D into RISAConnection. Now, one of the things that we're able to do in Risa 3D is just like we can define load combinations that are being designed for concrete or masonry or what have you, we can also define the load combinations that are going to be used in the connection design. And so if you wanted to do LRFD or ASD connection design, that's fine. You can choose to, do that. You could choose to omit certain connections or excuse me, certain load combinations if you want to as well. All that's possible. So you have the control to be able to do the different things in that case so that you can only look at really what you want to look at in that case. So again, I apologize for my computer being a little slow here. As soon as the project loads here, we'll go ahead and choose the director again and transfer into RISAConnection. There was a question just as this is loading. Somebody asked a question about Adapt. So maybe most people I'm sure know, but Risa recently, not super recently, but back in May purchased the Adapt family of products. And so right now we're discussing how to best integrate what really Adapt Builder with its concrete design, reinforced concrete and post-tension concrete slab design does in conjunction with what RISAFloor does. And so we're looking at the different options for how to do that, how to connect the products, or how to combine them into one product. And so we are evaluating that. Our development teams are working on that, and hopefully we'll have some kind of news for you just about what our plans are very soon. And so now with the model open here, I'm going to go to the director again and choose RISAConnection. So I'm just going to go ahead, and now when I do that, RISAConnection automatically launches. So we're launching into RISAConnection version 12. I'll just click OK here. And you can see here now that we have our connections open up. And so we can go ahead and start to evaluate various connections. And these connections are grouped, right? So I had multiple single column base plate connections. So we have those connections established, right? And so if I go ahead and click on one of them, I get kind of the grouping of this particular set of connections. And so I can also run and solve a group. So if I just solve this group, we can see, okay, both of these connections pass. So we don't really have any issues with them. If I wanted to change something, maybe I wanted to say, hey, I actually want a 6-bolt layout for these connections, and I want to see if that works here. Yeah, that works. I can go ahead and double click. If I double click to open this up, I can see the specifics here. So I can see, hey, okay, this is my 3D view. If I select something, say the bolts in this case, it automatically is selected in our Project Explorer, in our combinations. Additionally, we can also see our load combinations, right? So I can jump back and forth with various load combinations to see, okay, what's controlling in this case, right? What's the worst case axial shear moment, whatever, right? What's going on? And so we can see that data. We can also go ahead and look at our reports. So maybe this one isn't the most interesting one to look at. So let's go ahead and just solve the entire project. So I'll just solve the full project. And we're going to get some passes. So it looks like these column beam shear connections are passing. So that's great. But some of our others are failing. So let's look at our girder beam single angle connections. And so it looks like right off the gate, I would have been surprised that these were failing. But I see here that the unity check is less than 1 and it's failing. So generally in that case, it's a geometric thing. So in this case, we can see plain as day. All right, we have too many bolts, right? Our bolt number of bolts, goes through the connection there, or goes through the bottom flange of the beam. So I'm going to go ahead and make a selection for all. Since I'm in the group here, I can go ahead and make a change for all of these and say, okay, I want 2 bolts per row on the beam and 2 bolts per row on the girder. And then I can go ahead and resolve the group. And so when I resolve the group, the unity check goes up, but I do get a passing, passing thing. I can also go ahead and look at our base plate, or our brace connection here. So I've got this brace connection, right? This was that angle connection with our gusset plates. I've got our angles here in our beam. And so if we want to go ahead, I can see this in the 3D view, or I can look at it in a 2D view. This 2D view will give me just kind of a layout with the dimensions of exactly what's going on. Again, we have our load combinations that are all coming across here. So it's going to give us our controlling load combination. But let's look at the report to see, kind of what's happening here. So if I look, I can see most everything's passing, but I do have a bottom gusset brace connection problem. So if I look at, our bottom gusset to brace here, so that's top, bottom gusset to brace now, we have a geometric restrictions problem. And so basically, it looks like we have a problem with our edge distance, right? So, we need to make a modification to make sure that we don't have an edge distance issue in this case. And so here we can say, okay, maybe we need to, stretch this out. Maybe we need to add in a 5th bolt, so that we don't run into that edge distance problem, right? So if I make that change and then I rerun the connection, it passes now, because I had an edge distance problem I had too large of an edge distance between the last bolt and the edge of the gusset plate. So now if I jump back into my report, we meet the condition that the edge distance max has to be less than the minimum of 6 inches and 12 times the thickness of the gusset plate. We could have also increased the size of the gusset plate. And so really, this is kind of the final part, right? And I know not everybody does connection design, but this is the final part of this complete building workflow, in the sense that we're taking the information, whether it's the connection itself, whether defined in RISAFloor, Risa 3D, as well as the results, right? So the axial loads, the bending moments, the shears, all of that information that's coming from our superstructure model, bringing it into Risa connection for our connection design. And so the connection design, while it's not an optimization, you have control over just about anything that you could want, right? Plate sizes, the angle, you could change the number of bolts, the size of the bolts, the material of the bolts. You could change if you want it to be welded or bolted. All that is available. And so you could do that, and you can also use Risa Connection standalone, right? So it doesn't have to be used connected with a Risa 3D model. You could just come in here and have someone just completely on the side of the workflow doing Risa Connection design separately. And so once we're done, again, we want to kind of have this kind of confluence of everything that we're doing. We could come and use this export to Risa 3D button and send this back into Risa 3D. So I'm just going to choose export here. We'll export back into Risa 3D, and if I just open Risa 3D now, it's now telling me, hey, I didn't solve everything, right? So I didn't solve my problems that I had with my flange plate moment connections, but it's telling me that really my weld strength is the worst case. And so I can see this in a table, or we can look at this graphically, right? So I can come back to my home tab and turn on our connection results, and we can see this graphically. So we can see, yeah, we have a failure here, but here's we have passing here, we have some passing here. Obviously, if we look back in Risa 4, RISAFloor, we would see the passing for that Risa 4 model as well. And so that kind of brings us through the entire process. So, you know, we've gone all the way through, you know, we've gone all the way through from Revit to RISAFloor to Risa 3D and then into Risa Foundation and RISAConnection. I know we've gone a little bit long. We're just about 75 minutes now. And so I know Ashley has been answering questions throughout the time here. And so I think we'll go ahead and end our time here. If you have any additional questions, if there was something that maybe you didn't want to ask or something that you'd want to ask one of us individually, or if you're interested in just setting up your own demo, Ashley and I do what we call software tours, you know, multiple times a week with both current RISA users and people that are maybe new or investigating, you know, the design or the process, the workflow with RISA in totality. And so if you're interested in setting up a software tour, you can do that. One thing we didn't show in this workflow, and again, it's just part of the, from a time perspective, is we can actually go back into Revit. So we can, you know, at different stages of the design, go back into Revit. So for instance, like once we finish the gravity design with composites and stuff like that, if we wanted to send that information with reactions, number of studs, camber, stuff like that back into Revit, we would use the same feature in Revit. Instead of import in the add-ins, we'd use, or excuse me, instead of export, we use import, right? And we'd import the information from that same Revit, that same RISAFloor model. And so we want to make sure that we maintain that connection because that model was built in Revit. We'd want to maintain that connection back. We wouldn't want to import a new model or something like that. And so we are able to kind of round trip. And we have some other videos and some other documentation about round tripping from a RISA to RISAFloor to Risa 3D and then back into a Revit model. But we thank you for joining us today. We hope you enjoyed it. We hope you enjoyed Thanksgiving. Like I mentioned, the video for this particular webinar will probably be on our YouTube channel, either probably, I would say early next week, just with the holiday. And then the PDHs will also be sent out probably first thing next week. So if you have any questions in the meantime, please feel free to reach out to us, myself or Ashley, or you can just reach out to the general info account. Otherwise, have a great day and thanks so much for joining us.